Okay. Okay, perfect. Welcome everyone. Great to see that so many of you have joined, and it's my great pleasure to introduce Professor Lulu to kick off our e-seminar on scientific machine learning today. Lou is an assistant professor in the Department of Chemical and Biomolecular Engineering at the University of Pennsylvania. And he's an expert for scientific machine learning, in particular for physics-informed neural networks. And the goal of his research is to model and simulate physical and biological systems at different scales, which is definitely a very hard problem, to provide strategies for system learning, prediction, optimization, and decision-making in real time. He has just received the 2022 DOE Career Award. Congratulations on that. And today he's going to tell us about how to learn operators using deep neural networks for multiphysics, multiscale, and multifidelity problems. So please go ahead. I'm very excited for your talk.
Yeah, thank you, Ben, for the nice introduction. So in this talk, I will introduce some of our recent works on learning operators by using deep neural networks. So as we know, deep learning has achieved great success in the last 10 years on computer vision and also machine translation. However, the black box machine learning usually is not sufficient for scientific research. And also, the standard machine learning, especially deep learning, it requires a large amount of data set for training. However, this is not impossible in science and engineering. So in scientific research, we may have a special kind of data set, which I call 5D law data set. This could be dinky, dirty, dynamic, or even sometimes deceptive. However, on the other hand, in scientific research, we have this unique opportunity to incorporate the scientific domain knowledge into our machine learning model, including physical principles, constraints, symmetries, and also computational simulations. So in scientific machine learning, we aim to build the frameworks of machine learning to be accurate, robust, reliable, interpretable, and also expandable. So in scientific machine learning, usually we not only learn from data, but also from physics. For standard application, we usually have 3 types of problems. On the left, we assume we have lots of physics, but only small amount of data set. For example, if we consider we have the complete PDE of the physics or of the system, then the only data set we need is initial and boundary conditions. Then we can use the standard method, for example, find difference or find an element to learn or to solve the system. On the right, this is the standard deep learning or machine learning area. So we assume there's no physics, but we have a large amount of data set. Then we can train a big model to directly learn from the data set to discover what's the relationship between the outputs and the inputs. And here, in many cases, or in many engineering applications, we may have the applications in the middle, could be more important. So there's some data set, but it's too small to directly learn a system or a deep learning model. In the meanwhile, we also have some physics, but physics could be incomplete. For example, we do not have a complete PDE. We may have some terms of the PDE, but some terms could be missing. Or we may have the PDE, but we do not have the initial boundary conditions. Or there's some coefficients or parameters could be also unknown in the PDE. Then we try to combine together the data set and also the physics, but although both are imperfect and incomplete, but if we try to combine them, then we can have a good model for the system. So many methods have been developed for these kind of tasks. For example, the physics-informed neural networks, where we combine or we incorporate the PDEs into the deep learning model by using the loss function. And in this talk, I will introduce another type of the deep learning for the learning of physics and data set called deep neural operators. And especially, I will focus on one type of neural operator called DeepM&Mnet we recently developed. So usually when we try to use deep learning for a task, essentially we are consider the underlying function is mapping from a finite dimension D1 to another finite dimension D2. Then we know the neural networks is a universal approximator to any functions. Then we can use neural network to learn the function. For example, for the task of image classification, the input is image could be 20 by 20 pixels, which is 400 dimension. And its output could be a scalar or a vector. So this is in most cases, or in the standard scenario, what we do about the deep learning. So essentially it's function approximation or function regression. Now in this talk, I try to go beyond the function learning setup to the operator learning or operator regression. Here for the operator, I essentially means a mapping from one function to another function. So we go from this finite dimension space or vector space to this function space. And this function essentially is in this infinite dimension space. For example, the standard derivative operator. If we compute the derivative of xt, then the input of this operator is xt, the output is the derivatives. Then this is the operator is mapping from a function to another function. Or in that case, is integral operator. So the input is xt, the output is the integral of x with respect to some kernel k. Or if we consider a dynamic system or a PDE system, then the input could be the initial condition of the PDE or boundary condition of the PDE or the forcing term of the PDE. Then the output is the solution of the PDE either at a specific or fixed time t or in this entire space temporal domain. So all this kind of application or this mapping can be described by using the operator learning. Then when we try to go from function learning to operator learning, then immediately we have two questions. So the first question is whether we still have the guarantee of this universal approximation theory in operator setup, similar to the function learning. Then the second question is, if theoretically this guarantee of the universal approximation theory, then in practice, how should we design the network architecture such that the learning or the training would be efficient and the network would have high accuracy? So let me first introduce a few notations for the talk. Let's say the operator I try to learn is denoted by the symbol G. So G is the operator I try to learn. And the input is function called U, and output is GU. So both U and GU, they are functions. And here, let's first assume they are continuous functions. So this C means they are both continuous. Then for the output function GU, because GU is a function instead of a finite dimension vector, then Y is a point in the domain of GU, then GUY, which is the value of the function GU evaluated at the location Y. Then Y and GUY, they are finite dimension. Could be a scalar or could be a vector. So first, let's consider the standard supervised learning setup, which means we already have collected a data set of the pairs of U and also GU. So there are many pairs of functions. Now we try to have a network called G maps from the input U to the output GU. Then once we learn the network, then we can do the prediction for a new function, new input function U. So then let's start from this simple setup. Then we'll bring more and more the physics into the framework. Then for the first question of the universal approximation. So actually the answer is true. So it has been proved in 1995 that the neural networks is not only a universal approximator for functions, but also a universal approximator for operators, given some assumptions. For example, if we assume the underlying operator G to be learned is a continuous operator and the function space is compact and also continuous, then under these assumptions, they have proved that for arbitrary operator G and any epsilon accuracy, there always exists a neural network such that if the network is large enough, then the error between the ground truth operator G and the network prediction can be arbitrarily small than epsilon. So I will not go into details of the theorem, but essentially, this is the extension of the neural network approximation theorem from functions to the operators. So by the theorem, we know there always exists a network can predict the underlying ground truth. Then let's go to the numerics, or how in practice, how can we design the network architecture. So at first, instead of directly look at the details of the network, let's first look at what the inputs and outputs of the network. In a standard network learning, the input is a finite dimension vector. The output is another vector. Then it's straightforward to apply a network to transform the inputs to the outputs by layer. But here, the network input and output, they are not finite dimension vectors, they are functions. So it's not straightforward to input these functions to the network, or ask the network to output another function. So first, because the input U is a function, so we cannot take this function into this network in our computers. Then what we do is we have to have one extra step between this input function U and the network input. So we have to convert this infinite dimension function into a finite dimension representation. So for example, a simple case could be that we draw a mesh on the domain of input function U. For example, x1, x2, and xm, they are the nodes of the mesh. Then if the mesh is dense enough, then the function values on the mesh ux1, ux2, until uxm, they can be used to represent the input function U. Then this is a finite dimension, or actually a dimension of m. Then we can input this into the network without any problem. Or instead of using the evaluation of the function on the mesh, there are also other choices. For example, we could project the input function U to the Fourier series. Then the coefficients of the Fourier series or truncated Fourier series can be used to represent the function U. So there are multiple choices. This is just the most simple case. So this is input function. Then how do we handle the output function? So a similar idea could be we cannot output a continuous function directly. Then we can predict the function values of GU on another mesh, let's say y1, y2 until yk. So we only predict the output on some locations. It's doable, but it may have some issue, or it's not flexible. For example, on the right plot here, we consider we have a special data set or unperfect data set in the following setup. So for the first function U, we only have the location, or we only have the measurements of the output function GU on this location and this location, 2 locations. Then for the second input function U, we only have the output function collected in this location. This could be happen in a few cases. For example, the entire data set is not collected by the same group at the same time, but it could be one portion of the data set is collected by group 1, another part of the data set is collected by group 2, or different data set, different parts of the data set could be computed by different methods, one from find difference, another one from find element. So the measurements of the locations of the output function U, they are not aligned in the same location because they are generated by different methods and from different people. Then if we try to only directly output a finite locations, so this strategy cannot be applied to this kind of unaligned or irregular data set. And another problem is, in many cases, or especially in PDEs, we not only try to predict or we not only try to compute what's output of GU, we also would like to know what's the derivative of GU, what's the partial derivatives. Then if the output is only on a finite grid, then we have to have extra step of post-processing to compute all the derivatives. So this is not convenient and also would introduce extra numerical error. So we try to avoid any discretization of the outputs of the GU. So what we are doing is as follows. So in addition to use the U as the input, we also put the location Y of the output function as another input of the network. Then the network output is the function value of GU evaluated at the location Y. Then in this case, if we fix any U, then the GU is a continuous function with respect to the input Y, represented by this black box network here. Then we can compute the derivatives easily by using the back propagation or automatic differentiation. This can be also directly be applied to any kind of irregular data set because it's point-wise prediction for any input Y. We can also treat this method is basically measure-free for the output. So this is the inputs and outputs. Then let's look at what's the inside of the black box of the deep network. So in a simple case, we could use a standard network for this network, let's say fully Canadian network. But this will have a large error. So what we are doing here is we decompose the entire network into two components. The first component we call it branch net. So the branch net takes U as the input and outputs a latent vector B1 to BP. And we have another network called the trunk net. So the trunk net takes the Y as the input and outputs another latent vector T1 to TP. Then we merge or combine these two vectors to compute the output. And here, this merge operation we are choosing is the simple dot product. So the output, the GUY, is the dot product between this B vector and a T vector, or is equivalently is a summation of BK and a TK. So TK is only a function of Y, and BK only depends on the input U. So the TK essentially can be viewed as a basis function of Y for the outputs. And the BK is the coefficients in front of this basis function, but depends on the specific inputs of U. So this is the basic idea of the network called DeepONet. Then for the specific architecture of the branch net or trunk net, that is problem dependent. So usually for trunk net, because Y is 1D, 2D, or 3D, or 4D. So it's really usually low dimensional. So we can use the fully kinetic network as a trunk net. But for the branch net, it will depend on what the type of the input yield. We could use the standard network of fully connected, or if yield if the grid is a 2D grid and a regular grid, then we can use a CNN as a branch net, or we can use other networks, for example, the transformer. So now let's look at a simple case, a simple ODE case to demonstrate what's the advantage of the DeepONet by decomposing into two subnetworks. So this ODE is dy over dx equals to ut, as ux, with a zero initial condition. So we try to learn the operator G mapping from the ux, which is the right-hand side of the ODE, to the solution of the ODE. Or essentially, this ODE can be written as this integral, or the solution is the integral of the input u. So this is a very simple case. And let's look at the last column. This is the performance of DeepONet. We have a few versions of DeepONet with slightly difference, but only let's look at the last one. So we generate a data set for this ODE for different U and different S. Then we can train the DeepONet. Then the blue one is the training error, and the red one is corresponding testing error. So we can see the training error is small, so this is not interesting. What the important thing here is there's a small gap between training and the testing. So which means the network can generalize well from the training to the testing. As a comparison, if you look at other networks, for example, the standard fully connected network, that's a one network. So the training can be very small, but here we try to have the smallest testing error. So we did a grid search. So we try different combinations of network depth, network width, learning rate, and other hyperparameters. And the best performance we can find for FNN is shown here, roughly testing error is 10 to 94. And the corresponding training error is 10 to 95. So this is a large gap between training and the testing. Or we have also tested other networks. For example, this sequence-to-sequence learning by using LSTM. So LSTM works better than FNN. But still, the gap between the training and the testing is also large compared to the DeepONet. For this method, if we try to improve the testing accuracy, or if we try to reduce this generalization gap between training and testing, the most easiest way is we can increase the data set size. For example, if we use 10 times larger data set, then the standard method can work well. But for the small data set, DeepONet can have smaller generalization error. So this is the most simple case to demonstrate the advantage. Then let's go to a more complicated cases. This is a gravity pendulum with external force. So S is the location, S1 is location, S2 is the velocity of the pendulum, and we have external force UT applied on the pendulum. Then we try to learn the mapping from this external force to the solution. So the accuracy can be small, but here we try to see if we gradually increase the data set size from small to large, then we try to look at what's the convergence of the testing error and also the generalization error. So what we can see from the plot here is when the data set is small, the convergence is almost follows an exponential rate. Then when the data set is large, then it becomes a polynomial rate. However, this specific.
Can I ask one question?
Yeah, sure.
So didn't you mention you are using the transform network?
No, we are using the DeepONet, this network.
So BranchNet is implemented with ResNet or FNN or SIG-to-SIG.
Yes, okay. For this simple case, let's say ODE case or this grand pendulum, we use this standard fully connected for BranchNet and TrunkNet. But later, for some cases, we will apply CNN or ResNet.
Okay, I see. Thank you.
Yeah, for this simple case, we can use the simple BranchNet and TrunkNet. Okay, so this, but the rates, let's say, of the convergence depends on, for example, the network size. If we have a larger network, then we have different convergence rate, and also the transition location can also be different. But this exponential convergence also demonstrate the fast learning or fast convergence of the DeepONet. Or we can go to a PDE case, a diffusion reaction system, with this a force center. Again, here I also plot the convergence of the area in different cases. So the same thing as the previous example, but just another testing. So I will skip this one. So we have looked at a few PDs, ODs. So we have tested more cases, but let's go to another type of problem, stochastic PD. So here we have a stochastic PD showing in this equation here. So B here is a stochastic process. And in this case, we assume, okay, B is a different Gaussian processes from different correlation length L. So B is a stochastic process. Then for different B, we have the solution of U is also a stochastic process. Now we try to learn the G mapping from the B to the solution U. So mapping from one stochastic process to another stochastic process. So this is even more difficult than the function or mapping from functions to functions. Basically, we go one step further. So the theory of the operator learning is not valid here, or we haven't have a theory yet. But here we try to see numerically what's the accuracy. Because B is a stochastic process, it's not a function, we cannot input B into the network directly. Then the idea here we applied is we use a KL expansion, or we write down the B as a summation of the EI and the KCI. So EI is eigenfunction, and named I is eigenvalue, and the KCI are a random variable. Then by using the KL expansion, basically we split the random part and the deterministic part from B. Then all these EI, because they are functions, then we put E1, E2, En scaled by this the eigenvalue. We have N functions as the input of the BranchNet. And for the TrunkNet, in addition to have the physical space X, we also have the random space KC. Then we apply a DeepONet here. And after the training, this is the one testing case. So because B, or during testing, every B is a stochastic process, then U is not another stochastic process. And here I just plot the prediction for the same input B, but the 10 different realization of the stochastic process U. So we can have the good prediction for the prediction. Okay, this is the stochastic PD case. Now let's go to a more realistic examples. So this is the multiscale problem of the bubble dynamics. Let's assume we have a background of water, and in the water we have different bubbles of different sizes, from the small size bubble, which is nanometer, to the large bubble of the millimeter. Then if we change the pressure of the water as a function of time, then the bubble radius would also change. If we have larger pressure, the bubble becomes smaller. So when the bubble is large, then the relationship between the pressure and also bubble radius can be described by this equation called RP equation. When the bubble is small, this RP equation is not valid. We have to go to small scale particle simulation. So here we apply the dissipative particle dynamics to simulate the small scale dynamics. In the traditional methods, if you try to combine these two methods in two scales, then we have to design some kind of head shaking method. And here we try to use one DeepONet to learn the dynamics of the bubbles across two scales. So first step is we generate the data set by using P equation and also particle simulations. Then we try to train a DeepONet by using both data set together. So the input of the DeepONet is the pressure as function of T. And also we try to predict the bubble radius at location at time T for any initial location R0. And the issue here is when we generate data set by using two different methods, for the equation, we can easily run the equation for a long time. But we cannot run long simulation of the particle dynamics because it's really expensive. So which means for the small scale bubble, we can only run simulation for a short time. For large bubble, we can run simulation for much longer time. So the data set is unbalanced. Then this cannot be directly trained by the network because they are in the different regime of the scale. And here, but we know the physics. For the problem, actually we can compute the characteristic time scale tau c. Then we can rescale or normalize all the data set by the tau c for each case. Then we will have the same data set in the same scale. Similarly, we can do normalization for the space by using the initial radius of the bubble. Then after this data normalization by using the physics, then we can do the learning. Then after the training of the network, we can predict the bubble dynamics. Let's say for a large bubble, which is consistent with the RP equation. For small bubble, would be consistent with the particle simulation, which is the blue line here, because the particle simulation has the randomness. And in between, these three methods are consistent. Okay, the next example is we go from a small scale to a large scale problem. So let's consider we have a boundary layer problem. So we have upstream flow from left to right. And then here we have a boundary layer and it's high speed flow. And then we have a shock here. In addition, we consume there's some perturbation on the upstream flow. So it's not a steady state flow. We have a perturbation. Then we try to investigate how this perturbation from upstream propagates to the downstream. What's the downstream velocity profile? What's the pressure? So on the left, this is the few examples of the pressure on different locations. Here, each one denotes one sensor. And on the right, we have downstream velocity profile on a few different locations. So we can use DeepONet to learn the relationship from, for example, if we know if we have the sensors on the downstream pressure, then we can infer or predict what's the true upstream perturbation. Then from the perturbation of the upstream, we can predict what's the downstream velocity profile. So the learning is straightforward, but one issue here is if you look at the data set, it has multiscale on data set, some function is relatively smooth, but someone has the large oscillation. And to capture all these oscillations or different scales of data set, one method we applied is harmonic or Fourier feature expansion. So usually our network input to the branch net is location x and y. So we try to predict what's the velocity or what's the pressure at the location x and y. Then here, in addition to use x and y as network input, we also augment or incorporate the cosine and sine functions of the locations. So we have cosine pi t or cosine pi x, sine pi x, cosine 2 pi x, sine 2 pi x, cosine 4 pi x, 8 pi x, 16 pi x. So we have a few or several features of these Fourier features. Then these Fourier features can generate this high oscillated pattern of the solution much easier than if we directly only use the x and y as input. So this will help or accelerate the training of the network. There are also other types of extensions of DeepONet we have developed. So again, for the branch net, we have input Vx. Either at the first step, we can do the evaluation of Vx on a grid, or we can project Vx to a basis function. Then we can apply any network you like, FN, CN, RN, or other networks. Depends on the problem. Then for the trial net, in the previous case, we use a network to automatically learn what's the best basis function. But actually in the standard methods, or there are many methods we have developed in the past, then can compute a basis function from a data set. For example, we can use the PCA or POD. We can do a pre-processing to compute what's the POD modes of the data set. Then in addition to a network, we can combine these POD modes as another part of our trunk net. Then these pre-computed POD modes can accelerate the training a lot because the POD modes, although it's not perfect, but it captures the majority of the basis function.
Can I ask what POD stands for?
This is a proper orthogonal decomposition, or PCA is equivalent to PCA, is a principal component analysis.
Okay, thank you.
Or essentially, you are doing the SVD to compute the eigenvalues, eigenfunctions. So let's look at one example of this POD accelerated DeepONet or POD-DeepONet. So this is a Darcy problem. So the problem is not too complicated, but here we test the problem in this complicated domain. So it's a triangle domain, and then also we have a notch here. But as we mentioned before, the DeepONet is essentially mesh-free. So it can be directly be applied to this complicated domain without any modification. So we try to learn the solution of this problem from different boundary conditions. This is the performance of DeepONet, probably is 2%. Then the last column is POD-DeepONet. You can see it has even higher accuracy than the standard DeepONet by using the extra POD modes pre-computed. So this is another example which is more complicated. So we still have a high-speed flow from left to right. And also here we consider, in addition to the flow, we also have this chemical reaction. So we have a few concentrations of different species, N2, O2, and NO. So that's the rho 1, rho 2, and rho 3. So we have rho S, rho 1, rho 2, rho 3 for the concentration of 3 species. So this is the flow coupled with the chemical reaction. And also we have a shock here. This is high-speed flow. So for this problem, let's look at a specific example. So we have the initial condition of different pressure and a different density as the initial condition. Then we try to predict from the initial condition to the solution of pressure and also, for example, the density of N2 at the t equal to 0.0002. So this is one example of the testing case. So this dashed line is the initial condition of pressure and the initial condition of the density of N2. Then then t after the short time of t of 0.002, you can see it generates a discontinuity here, or almost a discontinuity here for both the pressure and the density, because it generates a shock. Then we try to test whether DeepONet can capture the shock well. So if we zoom in this, so first of all, definitely can capture the main flow or the pressure or the density. But if we zoom in to this shock location, we can see the DeepONet can also capture the location of its shock pretty accurate for both pressure and also the density. So for all the previous examples, we have discussed the mapping from one function to another function. So or from the space X to Y. Although the functions for the input and output, they could be a scalar function or vector function, but they are essentially a single function defined in a fixed domain. But in many cases, or for PDEs, if you try to predict the solution for different initial condition, boundary condition, and also force interns simultaneously. So we have different inputs. They are defined on different locations. And then the previous framework cannot work for this case. So we try to extend to this multiple input operator. So we consider we have x1, x2, and xn, n spaces as input, and y is output space. Then ki is a compact set in xi. So we try to learn the mapping from k1, k2, and kn, the product space to the output space y, or functions, n functions, v1, v2 to vn to the output u. So first, we proved that for this multiple input operator, the network can still be universal approximator, given similar assumptions as what we look at at the beginning. So this is an extension of the universal approximation from a single input to multiple inputs. And when we proved the theory, we applied this equation as a construction of the network. So we have n inputs, v1 to vn. So first, for each single input v, we need one network. We call it branch net 1 and branch net n. Then we have n outputs. These are n vectors. Then for the output of the TronNet, so f could be another network. So this is output of the TronNet for the input of y. Then this one is an n-dimension tensor. Then we do a tensor product between the f and also this n vector here. So this is what we applied to the proof of the theorem. But this tensor product is really expensive if n is high, because we have to go to high dimension tensor product. Then we can further use the low rank tensor approximation to reduce the network size. So instead of doing a tensor product, we do the point-wise or element-wise dot product between all these vectors. So if you look at the figure here, so we have n inputs v1 to vn. We also have the location y as input. Then we have n branch net and one TronNet. Then we have n outputs, n vectors. Oh, sorry, n plus 1 vectors. Then we do the element-wise product of these vectors. Then we do a summation of this the output of this element-wise product to compute what's the final output. So this extension of DeepONet from single input to multiple inputs. So essentially, we have n branch nets. So let's look at one example here, a divergent diffusion equation. So D is a diffusion coefficient, is a space dependent, and the 0, 0 is the initial condition. Now we try to learn the mapping from different diffusion coefficient and also different initial condition directly to the solution of the U. Then we can use the network we proposed. So this is called MIONet, multiple input DeepONet. So these are one testing case. So this is the dx, example of dx, and another example of U0x. And this is reference solution and our prediction. So the accuracy is around 1%. We also have other examples, but I will skip these examples here. So we have discussed many cases of single input and a single output, or could be multi-inputs. But here, let's look at a more complicated multiphysics problems. So this is electroconvection problem. Let's consider we have a 2D space. Then in this space, we have some fluid flow. We consider this is described by a Stochastic equation. We have the U is our velocity, P is the pressure. But in addition to the flow, we assume we have the charge, the particles in this domain. C plus and C minus are the concentrations of the positive and negative particles. Then due to this concentration of the particles, we will have electrical potential phi in this domain. Then we assume of electrical potential phi will generate a forcing turn on this source flow. So the fluid will be affected by the electrical potential. But in the meanwhile, the concentration of the particles will be also affected by the flow, by the velocity of U. So J is the flux. So you can see here we have a few different physics and they are coupled together. We have the flow, we have the transport, and we have the electrical potential. So we can again apply the standard DeepONet directly to this problem in a brute force way. So we generate a data set, then we do the training. But this could be expensive. So first, generating a data set for this problem is already expensive because it's a complicated problem. Then also, if you try to learn directly, it's expensive because we probably need a large network and a large amount of data set. Then what we try to do is as follows. So instead of learn this entire system directly, we first decompose the entire system into 3 components. So if we only look at the source flow, if we assume the phi is given, then the solution of U or P can be solved easily. And also the system can be learned easily by the network. Or if we look at electrical potential, if we assume we know the C plus and the C minus, then it's very easy to generate data set for this component and also for the training of the network. Then after we learned a few small components, then we try to merge them or couple them to construct the coupled solution. So this is one example of the data set for different boundary conditions. So delta phi is the electrical potential between the top wall and the bottom wall. So you can see this is the concentration of C plus, this multiscale at this location. So specifically here we applied 6 different DeepONets. So for example, so for the DeepONet G phi, the input is C plus C minus. If we know the C plus C minus, then it's very easy, we can easily to predict what is phi. Similarly, if we know the phi, then we can predict other fields, UVP, C plus, C minus. So in total, we have 6 DeepONets. And it's easy to generate the data set for each DeepONet, and each single DeepONet can be learned well, and they are independent. Then the second step, if we assume the 6 DeepONets are pre-trained and they are trained well, then how can we combine these networks to construct the coupled solution of the system in new conditions? So we have another network. This could be the standard network. The output is the solutions phi, UVP, C plus, C minus. Then we try to use these DeepONets as a constraint to all these outputs. So if we assume these 6 fields are already the correct solution or the true solution, then if we input the phi into GU, then the output is GU. Then this U prime must be consistent or must be the same as upstream U if they are already the solution. But when we have this randomly initialized network, definitely they are not the correct solution. So the output of this phi prime, U prime, V prime will be different from the UVP at the left. Then we have the loss function. So the loss function is the difference between this group of solutions and the outputs from the 6 DeepONets. So essentially, these 6 DeepONets are the constraint of the physics. Then we can do this in a full problem setup by introducing initial and boundary condition, or we can do the inverse problem setup. And here we assume we have some data measurements for these solutions. So we have some data loss. Then we can construct what's the solution by adding the data loss, and also this is this operator loss. So this is one prediction example. Let's assume we have the measurements of different fields on these scattered locations. Then by doing the training, we can construct the entire field of the solution. It's almost 1% accurate error. And the last part I will briefly discuss is this multifidelity learning. So in all the previous cases, we assume we have a single data set, which is an accurate data set. But in many cases, this could be difficult to generate a data set, even a single data set. And here, instead of generating a single data set of high fidelity, for example, from experiments, we can also, from using a low fidelity data set, for example, from simulations, then we have 2 data sets. One is accurate, but it's small. Another data set is less accurate, but it's large. And we try to merge or train a network from both data sets. So the TL is a data set from this low fidelity case. So we can have one network trained from, let's say, GL. The network is GL trained from TL directly because TL is large. Then we try to learn the high fidelity model GH by using the high fidelity data set. So here we have 2 ideas. So first, because we already have the prediction of the low fidelity network, then instead of predict what's a high fidelity, high fidelity solution, then we can learn the difference between the high and the low. So we assumed R is the GH minus GL, and R is another network. So if you look at the figure here, so we have 2 networks. One is high fidelity network, one is low fidelity network. So the high fidelity network predicts what's the low fidelity network predicts what's a low fidelity solution. Then this network, DeepONet Edge, predicts basically the correction term. Then we plus do a summation, we can predict high fidelity solution. And also, if you look at the network of DeepONet Edge, usually for the DeepONet, we have the inputs of the new function V and then location C. This is for branch and then for trunk. And then we have the outputs. But here, usually there's high correlation between low and high fidelities. So we can use extra inputs from the low fidelity prediction as the DeepONet edge. So now we have basically we augment the inputs, not only the new initial boundary condition, but also the low fidelity solutions, the GLV. So this is the entire network. So the prediction of the high fidelity prediction for new condition is equal to the prediction from the low fidelity plus a correction term. And for the correction term, in addition to the inputs of V or C, we also have the prediction, use the prediction of the low fidelity as the inputs. Or this is the diagram. So we have two networks, DeepONet L and DeepONet Edge. So let's look at one simple one example to demonstrate the efficiency of the method. So this is for the Boltzmann transport equation or BTE equation. So it's a high dimensional system. So we try to have the unknown is f mu here. So f mu is not a single function. So mu is the index. And here the index mu has the dimension of, or has 24,000 cases. So we have F1, F2, F3 until F 24,000. So it's really high, it's a large scale system. Although for each system, for each equation is not too complicated. Then F mu 0 is the summation or weighted summation of all these solutions. So it's a PD system of 24,000 equations. So we try to learn the solution of this problem, but we do not care about every single solution of F mu. We try to predict this J, which is heat flux. So J is a weighted summation of all these solutions. So this is the PDE. And here we try to predict the solution of the PDE for different geometries. So let's say we have a 2D domain and then we have a 5x5 grid. And each location on this blue color can be a material or can be a pore. So for example, in this case, this one is a pore, this one is another pore. Then this is the solution of the J. And this is another geometry. So in total, actually, we have 2 to the power 25, which is 3.4 times 10 to the power 7 different possibilities of different geometries. And for the data set, we have 1,000 solutions, which are accurate solution from the numerical solution. And we have another 10,000, which is less accurate numerical solution. So the accuracy of the low fidelity is a dashed line. So what roughly the mean square error is 10 to the negative 2. So you can see it's really a low accuracy. And if we train the network only from the high fidelity solution, if we only have 1,000 solutions, then the accuracy is 10 to the negative 3. But if we merge the high and the low data sets by using this multifidelity DeepONet, we can have one order or magnitude smaller error compared to only using the high fidelity solution. And this is the prediction for new condition or new geometries. So you can see roughly the 2% accuracy. So this is the summary of what I mainly discussed today. We start from the standard DeepONet for operator learning, then discussed a few extensions, POD-DeepONet or MIONet, and for different applications, with a little bit discussed on the theory part. So all these methods can be applied or can be developed by using the software called DeepSD. Also, DeepSD is the software for physics-informed neural networks. So it has been used by many papers and researchers. And also you are welcome to use this library to implement either operator learning or physics-informed learning. And it's also open source, and you can easily modify the source code to develop new methods. This is the last part. Thank you for your attention.
Thank you so much for this wonderful talk. It was really great. And I really liked all these really nice examples illustrating multiphysics, multiscale problems. I'm working a bit on those problems as well, but it's indeed a very hard problem, and we have some very nice results here. We have a bit time for questions, a few minutes. So just ask your question straight away. Otherwise, I start with a question. So you have this POD-based DeepONet. Intuitively, I'm wondering why you want to kind of compute first the POD modes to project your data and feed then these latent variables into your neural networks. Because if you do this, you destroy kind of the nonlinearity in your data, right? So why using a linear projection rather than a nonlinear projection? Like you could have instead like some nonlinear encoder there. So is there a good reason? Do you get anything from doing it or using a linear projection?
So yes, so the linear projection definitely is not perfect. But one thing is, if we do the standard, or if we only use the neural network, ideally it could work, but the training could be expensive. Sometimes the training could be slow. By using this, or you can say knowledge or information from the linear POD, basically this can accelerate the training. Or if we assume we try to learn a simple function or selected function, but if we have a linear profile of the function, the network only learns the high frequency component or as a correction. So basically a POD can accelerate the training of the network or make the network learns faster.
Okay, sure. That makes total sense. Okay, as a way to accelerate training. Yeah, that's interesting.
Yeah, but of course we can apply other techniques.
Yeah.
POD is just most simple case. We can apply more complicated methods.
Okay, that's good. Maybe a second question, what I was wondering a bit, as you showed like the comparison at the beginning to sequential modeling, ResNets, fully connected neural networks. Why? I'm just surprised, like seeing a ResNet here and it performs relatively poorly, where typically like residual connections lead to state-of-the-art results in CV NLP applications. Do you have some intuition why ResNet? So have you like here, did you tune the epsilon like for the residual step, or did you just set it to 1, which maybe leads to a better approximation in this?
Yeah, that's a good question. So usually ResNet is better than the standard network, especially when the network is deep. But here, one thing is, for this problem, actually you can say this problem is the most, the simple case we have. Yeah. We can have in all the OD or PDs. So for this simple problem, the ResNet probably is not necessary. So by using because the network actually is pretty shallow, only a few layers. Another thing I also mentioned. So in this case, when we do the experiments, actually we did set the coefficient to be 1, which is the standard ResNet. We didn't use the or pick another could be a better epsilon in front of residual connection. That could be further improved, but here we use a simple case.
I see. I mean, because like particular for this problem, right? I mean, I think like, I mean, I'm particularly interested in ODE nets or neural ODEs or whatever you want to call them, and they should work very well for this case in combination with some higher order integrator. I guess so. It would have just been interesting to see this as an additional comparison. But okay,
yes, by using some more improved version or modification of ResNet, it could be have much better improvements, but here is the simple case. Yeah.
Oh, okay, that's fair. Just curious. Are there any other questions? Okay, go ahead.
Hi, Lulu. This is Paul from Pitt. I was wondering if your DeepONet offers information in terms of the interpretability of the operator or the interpretability of the actual function. Are you able to provide like an explicit, some sort of explicit form or some sort of explicit functional dependence?
Yeah, this is a good question. So in this talk, I didn't explain or open the black box of DeepONet. What is ChalkNet doing? What is the BranchNet doing? But this is another work by panels students from the PNNL. What they are doing is they first train a DeepONet as a black box. Then they try to understand what is the what is the ChalkNet is really doing here. So what they are doing is after the training, you can just remove this branch net or fix the branch net and only take the remove the branch net and only take the ChalkNet. So you can see the ChalkNet basically is a basis function of the y. Then we have a p basis function. So during the learning, the basis function can be pretty arbitrary. Then they do one further step. They do this. They do some normalization and orthogonal to make sure these p functions has norm one and also orthogonal to each other. Then basically they can discover or use this network learned basis function for other cases. For example, we can to replace the standard basis function in the spectral methods, and they found that this network learned basis function actually works much better than we manually picked the basis function for them some polynomial basis. So this could be one way to understand. So what do we have learned in terms of basis function? Actually, they have some very nice plots.
Okay, thank you.
Hi, is there a reference for that last paper that you talked about?
It's not in my slides, but if you search the panels stinners from PNL, I think the paper title is Machine Learned Basis Function for Spectral Methods, something like this.
Okay. And related to that, is there like, so what happens if I remove the trunk net and just append the coordinates or the square locations to the branch net as like a different channel or something? Is that possible? Because there are like this other class of networks, neural operators, and they don't really have this branch net, trunk net, and they report good results. I was wondering what you think about that.
Yes, yeah. Actually, it's possible to do. So we don't have to have this explicit branch net. We just put this y, let's say, as another channel in this at the U. So U is one channel. Let's say if 2D images, we have 2D domain with a grid, and U is one channel, one image. The y coordinates is another channel. Actually, this has been done in some other methods. So this could work. But one issue is, as we discussed here, in this way, actually, we have a discretization for the output. So we can only predict the outputs on this grid. So it's not match-free, and we cannot handle this in unaligned or irregular data set, or we cannot apply the back propagation to compute the gradients directly. So it's doable, but it's less flexible for some cases.
But if I had y as the input, I can still compute the gradients with backplot, right? Because the gradients are with respect to the location.
So if we do the channel way, so if it depends on how do we pick this network here, because if we use the standard network, then because it becomes a channel, so all the coordinates will be masked. But there's some way to do it, but it's less convenient. So here is really easy to do, to compute the gradients.
Right. And then when you say that, DeepONets are mesh-free in general, but your training data comes from some PDE solver that's defined on mesh, right?
Yes.
So do you actually learn dynamics that are not present in the training data? I mean, because if your data comes from some mesh, is there any reason why I wouldn't also want my query locations to be on a mesh? Wouldn't that just be easier?
Yes, let's say if the data set is totally in a fixed common mesh, then you can predict, or you can learn the network to only predict location, the prediction on these mesh locations. It's then could be fine. But again, in some cases, for example, the last example, the problem we try to do is we try to learn from different geometries to different solutions. Then these geometries does not have a common fixed mesh. Right? If you do this problem, usually with a triangle mesh, then all the data sets, they are unaligned.
Right. Okay.
So there are some applications like this.
Okay. Yeah. Thanks. Thanks a lot.
Okay. Let me thank you again for this great talk. And thank you for joining all. And I guess that's a good point to wrap up.